In this tutorial, I'm going to illustrate how to use a truth table to explore the concept of logical equivalence. So a good starting point for us is to differentiate between logical equivalence and material equivalence. So you'll recall from our discussion of our five operators that material equivalence is sometimes called a biconditional, or has drawn with a double-sided arrow. The biconditional or material equivalence is an operator. So as an operator, it takes an input on one side and an input on the other side and gives us a particular output. And from our definition of the material equivalence operator, in other words, a truth table, you know what those values are. Essentially, if P and Q have the same truth value, no matter whether it's true or false, the same truth value yields true. And if they have different truth values, then it yields false. So that's the material equivalence operator. The concept of logical equivalence is different in that logical equivalence is a property of two or more different expressions. So let's consider two expressions to illustrate this point. Let's have a look at P implies Q. That's one expression, and another expression is not P or Q. All right, these are two different expressions. What we want to know is how these two expressions behave when we give them the same inputs. In other words, the same value for P and Q. What happens? So to explore that, we're going to construct a slightly extended version of a normal truth table. And the first thing we'll do is look at these two expressions and determine how many unique variables there are. So there are two. There's P, it's used twice, and Q is used twice in these two expressions. So now from here we want to construct what is essentially a normal truth table. So we have to lay out the input values under P and Q. So how do we do that? Well, we always start with 2. That's our base. We have two values, true and false. We have two distinct variables, so that's the power you raise it to, so that gives you 4. So now we know that there need to be 4 rows. So we can create those rows, alternating first by 1s, true, false, under P. Then in the next column, we have alternating by 2s, true, true, false, false, will be the values for Q. So now we've created input values. Let's calculate the output values for these two expressions. We'll start with this expression. It has only one operator. It's binary, so it branches twice, but notice there are no other operators. So all we have to do is calculate the output value for material implication. So for the first row, when P is true and Q is true, P implies Q is true. For the second row, when P is false and Q is true, P implies Q is true. For the third row, this one is different. When P is true and Q is false, P implies Q is false. And for the fourth row, when P is false and Q is false, P implies Q is true. All right, that takes care of that level 1 operator. And so these are the values of this expression for all the possible permutations of inputs. In other words, all the values that P and Q could take together. So now let's turn our attention to this second expression. Here we have a major operator, the disjunction, and it branches as binary operators do, 2 branches. Over here on the Q side, we have no further operators, but over here on the P side, we have 1 operator. So that's our level 2 operator. So we're going to want to calculate the output for our level 2 operator first so that we can feed that value up to the level 1 operator. So for the first row, when P is true, not P is false. If P is false, not P is true, false, and true for those rows. Now, what we need to do is give the value of the level 2 operator, not P, on one side, and the value of Q for each row on the other side to this OR, and that OR is going to give us an output. So for the first row, not P is false, And when you look up Q over here, it's true. So false or true yields true. For the second row, not P is true and Q is true. So true or true gives us true. For the third row, not P is false, Q is false. So false or false gives false. And for the last row, not P is true and the value of Q is false. So the output is true or false. That gives us a true. So now we're finished with the level 2 values. Now, what do you notice about these two expressions? For the same inputs for each row, they have the same output. So for the first row, if P is true and Q is true, then these two expressions yield the same output, which is true. So this is what we mean when we say that an expression is logically equivalent. Two expressions are logically equivalent when, for the same inputs, they yield the same output truth value, whatever it may be. So when you look down each one of these rows, you see that for whatever the input is, these two expressions yield exactly the same output. Now, let's talk about the connection between logical equivalence and material equivalence, that operator we talked about at the beginning of this tutorial. So let's take our two expressions, P implies Q and not P or Q. We already know that these two expressions are logically equivalent. So what happens when we place the material equivalence operator between these two expressions? Well, if you think for a moment, you'll realize that if the two expressions, P implies Q and not P or Q, always have the same truth value, then it becomes apparent that if you join these two together with a material equivalence operator, the result is going to be all truths because these two expressions always have the same truth value. So one way we could think about logically equivalent propositions is that if you join these two propositions together, you get a material equivalence proposition that's always true. And we have a term for propositions that are always true. They're called tautologies. So if you take two logically equivalent expressions and you join them together with material equivalence, you get a tautology. So try this yourself. Think of some expressions like P implies Q, not P or Q, and construct a truth table to test out whether they are logically equivalent. If they are, construct another truth table that joins these two expressions together like this with a material equivalence operator and show that that this operator joining two logically equivalent expressions always yields a tautology.